Hey everyone, welcome to Pytechie. Recently, I went through an interview where I was asked to implement KNN from scratch. That's when I realized that interviewers are no longer just about DSA, they are also testing your understanding of core machine learning concepts. So, in this series, we are going to break things down by step and build everything from scratch. If you really want to understand how these algorithms work under the hood, this series for you. Let's get started. Have you ever wondered how a machine learns to draw a perfect line through data? That's exactly what linear regression does. First, understand the problem. Define what you want to predict and identify the factor that influence it. Then gather the data, handle the missing values, and prepare the feature for training. Next, explore the data, analyze the relationship between variables, detect outliers, and check for linear trends. Next step, split the data sets. Divide the data into training and testing set to train and evaluate the model properly. Now let's choose the model. Select the linear regression equation that best fit your problem. After that, we'll train the model. The algorithm learn from training data and find the best fit line by minimizing the error. After training the model, we'll evaluate the model, measure the performance using metrics like R squared, mean square error, and mean absolute error. Next, we'll make the prediction, use the trained model to predict output for the new or unseen data. Check assumptions, verify important assumptions like linearity, constant variance, and normal distribution of errors. After that, if you find you want to improve the model, you can improve the model by optimizing the performance by refining features, removing outliers, or using advanced technique if needed. This is the linear equation used to determine the line of best fit y equal to mx plus b, where y is the predicted value and x is the input feature, m is the slope of line or weight, b is the intercept or bias. In this video, you can see some places y prid and somewhere you can see y cap. So both are explaining the same thing. So to calculate what's wrong with our data, so first we will calculate how wrong our prediction by using y minus y prediction for this single data point. Now we know y prid is nothing but y equal to mx plus b, so we can replace y prid with the mx plus b. Now to avoid a negative value, we use the square here to avoiding the negative values. So by this way, we square the error so negative and positive mistake don't cancel out. Now we average all the error to form the mean squared error or cost function. Formula is simple 1 upon n summation of y minus y prediction square of. Now in same cost function, we replace y prediction with the actual y prediction values, which is nothing but y mx plus b. Now we have to minimize this value of the cost function. We will apply the derivatives. Now here we will calculate derivative with respect to m. So it's nothing but the dj upon dm, the cost function. We will apply the derivative of n. The derivatives tell us direction in which the slope should move to reduce the error. Here we apply the derivative. After applying the to apply the derivative, we remove the constant outside the square bracket. So 1 upon n is outside the square bracket, and then remaining part we are applying the derivatives. So once you apply the derivative of u square is nothing but 2u, and then we can again apply at the u values, which is nothing but y minus mx plus b, and then we all the values here y and b are the constants, so m is nothing but 1, so we will get the final value is minus x. Now we will substitute back again the values, and we will get the final value, which is nothing but a minus 2 upon n summation of x y minus y squared, y minus y cap. So this is with respect to m. If you apply the same derivative with respect to b, so we get the different equations. So you can remember this equation. Once you will apply the once you will start the coding, you can use this equation inside the code. So remember this equation. Finally, dj upon dn is equal to minus 2 upon and summation of x, y minus y cap. It's time to implement everything in code. We will now build linear regression step by step using Python and NumPy. We will train a model using gradient descent, visualize the regression line, track the log regression, evaluate the performance using standard metrics like mean squared error, root mean squared error, mean absolute error, and R squared. So first we will install the required libraries, which is nothing but a Matplotlib and NumPy. So Matplotlib is for the visualization purpose to visualize the charts and graphs, and NumPy for the mathematical computation purpose. We are using the NumPy. So first we will import the NumPy, then second we import the Matplotlib. So it is nothing but a import matplotlib.pyplot as a PLT. Now we'll create a linear regression from scratch. We have created one class, linear regression. Inside this class, we have one constructor class. In the constructor class, we have a learning rates, epochs, and M nothing but is weight, and B is nothing but a bias, and losses to store the loss values. So these are the nothing but the hyperparameters. Here, learning rates control how long each gradient descent update step will be. So it is smaller, by default is 0.01, and like inside this class I have declared the default value is nothing but a 0.01, and epochs is like nothing but determine how many times a model will iterate through the training data. So here I have given default 100 values. Next we can calculate the loss, which is nothing but a y minus y predicted values, and we are taking the square of that to avoid the negative values, and then after that we are applying the we are taking the average of that, means nothing but a average. Now after that computing the loss, we are creating the function called predicts. Predict is nothing but a y equal to mx plus b, where m is the same weight and x is the that feature and b is the bias. To predicting any y values, we are using this equation mx plus b. Now in the fit function we have n is nothing but a number of sample data, and for the each epochs will predict the values and will calculate the gradient descent with respect to m and b. So here we have taken the derivative of d of m and derivative with respect to d of b of the cost function. So here we have multiply by x measure how strongly each feature contribute to the error. The negative shall ensure the gradient descent move in a direction of lower loss. The compute of derivative with respect to the intercepts b, unlikely the m intercept does not multiply by the x. So this is the only difference between the db and dm, is we are in dm we are applying multiply with the dx, and here we are not multiplying with the x. Now we update the slope and its intercepts, both the parameter. So the gradient descent subtract the gradient multiply by the learning rate. They gradually move the regression line toward the best fit. After updating the parameter, we calculate the loss and store it. So here we are calculating the store or loss, and we are storing in the losses list values. After every 100 epochs, we are printing the epochs values and the loss values. Now we write here the function to visualize the losses. Here in x we have a loss and y label we have a loss. X have a epochs and y have a loss. Now we have initialized some x and y values. X y is nothing but a double time of x. So 2 is nothing but a double time of 1, like that way. I have created this sample data here. Now we initialize the linear regression scratch or class here. A learning parameter we have passed 0.01 and epochs is a thousands. So if we pass the learning rate 0.01, that will override the value of this, and epochs also will become a 1000 now from 100. And we call the fit parameter, and it will be update the we'll see the updated slopes and its intercept values. After that we'll check the predicted value on that, and we'll plot the scatter plot on this one. Here you can see the in scatter in this plot we can see the uh, yellow line is nothing but sorry, blue dot is nothing but data points, and red line is nothing but the our base fit line for the data. Now this is the loss curve also. You can see this is properly loss curve. So this is nothing but we have a very few data points. Because of that, you can see this base fit line. Otherwise, not be that much fit. It should be a some kind of overfitting problem it will create. Now we will evaluate the model. So this is nothing but a mean square error and root mean square error, mean absolute error. These are the metrics we are taking and R square values. So base metric to evaluate the linear regression model is nothing but the R square. So if the value is closer to 1, thus R square value is closer to 1, that means your model is performing very well. So here I have passed some test parameter when test values like 7 and 8. So expected outcome will be 14 and 16. So it will be evaluate and predict the values of that, how much it is performing. So here you can see the R square values is nothing but the 1, closer to 1, which is the best fit line. The training error is somehow similar to the test error. So that means our model is performing good. But if training error is more than the testing error, that means our model is getting the overfitting problem. If the training error is high and the testing error is also high, that means your model is in underfitting problem. So you can remember these things. Now we have completed implementation of linear regression from scratch using gradient descent. This project demonstrated the core mathematics behind the machine learning without relying on the external libraries. By building everything manually, we gain a deeper understanding of optimization, gradient, and model training. Thanks for watching this video. If you found it helpful, don't forget to like, share, and subscribe for more machine learning and Python content. See you in next video.